7 people are dead in Indiana. 1 person is dead in Hawaii. More than 117,000 customers remain without power. Homes have been ripped from foundations. Bridges have disappeared. Roads have collapsed. And rivers have crossed levels that had not been seen in more than a century. And the most unsettling detail is that these are not 2 versions of the same storm. They are 2 completely separate disasters, roughly 4,000 miles apart, unfolding during the same weekend. One began with thunderstorms over the Midwest. The other arrived with a tropical cyclone near Hawaii. Yet both produced the basic threat: extraordinary amounts of water overwhelming systems designed around assumptions about where the water should stop. In Indiana, the crisis began on August 11th, when repeated rounds of severe storms moved across the state. Some locations received more than 11 inches of rain in only a few days. Newcastle recorded 11.43 inches, while Greensburg received more than 7. Those numbers are already dangerous. But the rainfall became far more destructive because the ground was saturated before the worst storms arrived. Indiana had already absorbed repeated heavy rain. The soil had little capacity left to accept another deluge, so an enormous share of every additional inch became runoff, rushing towards streams and rivers instead of disappearing underground. That distinction explains why rainfall totals can sometimes underestimate the real danger. 11 inches falling onto relatively dry ground is not the same event as 11 inches falling onto ground that is already full. Once infiltration collapses, the landscape effectively becomes a conveyor belt carrying water toward the drainage network. Roads become channels. Fields become temporary lakes. Small streams rise rapidly, and the water eventually concentrates inside major rivers. That is what happened along the White River, where flooding spread from Hamilton County toward communities north of Indianapolis and into neighborhoods that suddenly looked less like streets and more like waterways. Drone footage from Indianapolis showed the scale of the transformation. Floodwater surrounded houses, climbed toward front doors, and covered vehicles so deeply that some cars were visible only as dark shapes beneath the surface. Residents in affected neighborhoods used kayaks and small boats to move through places where people normally drive, walk dogs, or collect their mail. The Indianapolis Fire Department alone reported pulling 95 people and 45 pets from floodwaters by Saturday afternoon. That single number gives a sense of how quickly an extreme rainfall event can turn into a rescue operation across an entire urban area. Then the White River crossed a line that transformed the disaster from a major flood into a historical event. At the Anderson Gauge Station, the river crested at 24 bars 93 feet on Friday, August 14th. The previous record was 23.6 feet, established in 1913. That means a record that had survived 113 years was exceeded by roughly 1.33 feet. At Noblesville, the river also challenged the old 1913 benchmark. This was not simply another flood added to a long list. The measurement used to describe the worst flood in living historical memory had just stopped being the worst. The year 1913 matters because that flood was itself extraordinary. It struck in late March, when heavy rain combined with melting snow across the region. Between 6 and 11 inches of rain fell across parts of Indiana, Ohio, Pennsylvania, and Kentucky, while snowmelt was adding even more water to rivers and soils. In some places, the ground was still partially frozen, limiting infiltration. The result was a massive hydrological load that produced catastrophic flooding and an enormous death toll. The 1913 flood became the benchmark against which later Indiana floods were judged for more than a century. And now that benchmark has been beaten by a summer event. There was no snowpack feeding the rivers. There was no spring thaw. There was no frozen ground, creating an additional barrier to infiltration. Instead, a sequence of thunderstorms repeatedly delivered rainfall onto land that was already saturated. That difference is what makes the new record so important. It does not mean the 2 floods were meteorologically identical, but it shows how efficiently a prolonged rainfall pattern can load a river system when storms keep returning to the same basin. The atmospheric setup was surprisingly understandable. A frontal boundary formed across the Midwest and essentially stopped moving. Warm, humid air pushed northward from the Gulf of Mexico, while cooler air remained farther north. Neither side displaced the other enough to clear the boundary. At the same time, a high-pressure system over the Gulf helped feed warm, moisture-rich air northward. Disturbances moving along the jet stream repeatedly triggered thunderstorms along that stalled boundary. The atmosphere kept supplying fuel, while the boundary kept the storms focused over the same general region. Meteorologists call one important aspect of this process training. Imagine a line of storms moving over the same section of ground, like train cars passing along one track. The first storm drops a heavy load of rain. Before the landscape can drain it, another storm arrives, then another. The individual cells do not have to be extraordinary by themselves. The danger comes from repetition. When the atmosphere keeps rebuilding storms upstream and sending them across the same counties, rainfall totals accumulate faster than rivers, drainage systems, and soil can respond. The geometry of the storm track becomes as important as the intensity of each storm. The human cost was severe. At least 7 people died in Indiana, although the total remained subject to change as recovery operations continued. Among the victims was 18-year-old Matthew Morey, an incoming Purdue University freshman whose body was recovered after he and 3 friends entered the Mississinawa River as flooding was beginning. A 4-year-old boy in Jennings County died when a tree crashed through his home during strong winds. Other victims included adults in several counties across northern and central Indiana. These were not abstract statistics. They were people caught in an event that developed across ordinary communities. Indiana's response also revealed another layer of the crisis, the difference between emergency response and long-term recovery. The governor declared a statewide disaster emergency, and a federal emergency declaration made assistance available. But an emergency declaration is not the same as a major disaster declaration. The emergency mechanism is designed to support immediate operations, such as moving people, equipment, and resources, while the threat is active. It can provide up to $5 million in federal resources. A major disaster declaration can unlock broader assistance for damaged homes and infrastructure, but reaching that stage depends on preliminary damage assessments. Officials have to document damaged buildings, roads, utilities, public facilities, and other losses across affected counties. Until that process produces a clearer picture, the immediate federal response remains smaller than the potential rebuilding bill. And the flooding was not confined to Indiana. As the weather system moved east, communities in Ohio also experienced serious flooding. Firefighters in Perry County alone carried out more than 50 water rescues over Saturday night and into Sunday morning. The disaster was becoming regional. But thousands of miles away, another water disaster was unfolding for a completely different reason. Hurricane Lala strengthened from a tropical storm into a Category 1 hurricane on August 15th as it approached Hawaii's Big Island, with maximum sustained winds of about 75 miles per hour. The eye passed near the southern tip of the island without officially making landfall. That distinction matters because a direct hurricane strike would have represented a major historical event for Hawaii. Yet, Lala did not need to cross the coastline to produce devastating consequences. The defining threat in Hawaii was not simply wind, it was rainfall. In the heaviest bands, rain fell at rates of 3 to 5 inches per hour. Some locations received more than 2 feet in a single day. The mountains of Hawaii Island received more than 3.5 feet, or over 42 inches, while mountainous areas of Maui saw up to 2 feet. Forecast totals were revised upward as the storm slowed, and that slowing was critical. When a tropical system moves more slowly, it can keep releasing enormous amounts of rain over the same terrain for longer periods. The Big Island's geography amplified the danger. Moist air was forced upward by steep volcanic mountains, encouraging intense rainfall and concentrating runoff toward lower communities. Officials reported that occupied homes may have been swept from their foundations in parts of the south. Emergency teams launched search and rescue operations involving county personnel, the Hawaii National Guard, and the Coast Guard. Some people had called 911, but could not immediately be reached because floodwater and boulders blocked roads. In darkness, responders were dealing with rushing water, unstable routes, and communications problems as cell towers went down. The damage spread far beyond individual homes. More than 100 homes on Hawaii Island were damaged or destroyed. 6 bridges in the Kau area were destroyed or nearly destroyed. A section of Pahala Highway collapsed, cutting off a critical route near an area served by one of the region's hospitals. The collapse even created a new waterfall where the road had been. Airlines canceled dozens of flights, while many more were delayed. Schools, government offices, courts, and other public facilities closed as communities dealt with damaged roads, dangerous conditions, and disrupted services. Then came the power crisis. By Saturday night, more than 88,000 Hawaiian Electric customers had lost electricity. By Sunday morning, the number had climbed above 178,000. By Monday, approximately 117,000 customers remained without power across 3 islands, with tens of thousands on Hawaii Island alone. The utility warned that some outages could last months rather than days. That sounds extraordinary until you understand the basic geography of Hawaii's power system. The islands are not connected to one another by a continental-scale transmission network, and they have no road linking them to the mainland. On the continental United States, a major outage can trigger mutual aid from neighboring utilities. Repair trucks can travel hundreds of miles overnight. Replacement equipment can move along highways. Crews can arrive with specialized tools and supplies. Hawaii does not have that luxury. Every crew member, transformer, pole, and piece of transmission equipment is either already on the island or must arrive by ship or aircraft. Hawaiian Electric requested outside personnel, with approximately 100 mainland utility workers expected to arrive to support repairs. What might be a logistics problem on the mainland becomes a geographic bottleneck in an island environment. The consequences of a prolonged outage multiply quickly. Water systems depend on electric pumps, which is why authorities issued restrictions limiting water use to essential needs such as drinking, cooking, and personal hygiene. Refrigerators lose power, threatening food and temperature-sensitive medication. Communication systems can degrade, including the cell networks people rely on to call for emergency assistance. Generators can provide temporary support, but they consume fuel, and fuel itself has to reach an island. One broken system can therefore push several others toward failure. The disaster becomes a chain reaction rather than a single event. At first glance, Indiana and Hawaii appear to have nothing in common. One involved a stalled frontal boundary and repeated thunderstorms. The other involved a tropical cyclone near a volcanic island chain. There was no single weather system connecting them, and there is no scientific basis for pretending that one caused the other. But there is a meaningful connection. In both places, the primary destructive force was not simply wind. It was the enormous volume of water concentrated over vulnerable terrain and infrastructure. That brings us to one of the most important lessons from this weekend. Accurate forecasts do not automatically produce safe outcomes. In Indiana, forecasters warned that the White River could reach major flood severity and communicated that the worst conditions had not yet arrived. In Hawaii, the National Hurricane Center warned of life-threatening conditions, while the electric utility warned customers about the possibility of prolonged outages. The warnings existed, the science was functioning, yet people still died. Homes still disappeared, and more than 100,000 customers remained without electricity. The gap between an accurate forecast and a safe outcome is often an infrastructure problem. It involves where homes are built, how floodplains are mapped, how roads cross rivers, and how much margin communities have when a record is exceeded. It also involves how people interpret warning categories. A Category 1 hurricane is defined by sustained wind speed. It does not tell you how much rain will fall, how quickly water will rise, or what steep volcanic terrain will do to that water. Category 1 means a specific wind range. It does not mean low overall risk. There is also a dangerous misunderstanding surrounding the phrase 100-year flood. It does not mean a flood happens once every 100 years. It describes a flood with roughly a 1% chance of being equaled or exceeded in any given year. Two such floods can happen close together without violating the statistics. But those probabilities are built from historical records. When an old record is shattered, especially by a mechanism that differs from the event that established it, the historical sample becomes harder to treat as a perfect guide to the future. That does not prove that every flood will now become larger, and it does not mean existing maps are automatically useless. It does mean that communities have to ask whether their assumptions still provide enough safety margin. Every levee height, drainage capacity, culvert size, floodplain boundary, insurance calculation, and building standard reflects some estimate of risk. When reality pushes beyond the historical benchmark, those estimates deserve another look. As of August 18th, Indiana's water was beginning to recede, but recovery was only starting. 7 deaths had been confirmed, damage assessments were underway, and officials were determining the scale of losses that could shape future federal assistance. In Hawaii, roughly 117,000 customers remained without power. Major transmission repairs had begun, and mainland crews were preparing to support the island workforce. More than 100 homes had been damaged or destroyed, bridges had failed, and the highway collapse continued to disrupt access. Hawaii also carries a different kind of vulnerability: memory. The state's last hurricane landfall was Hurricane Iniki in 1992, a Category 4 storm that killed 7 people and caused billions of dollars in damage in the value of that time. Nearly 34 years later, an entire generation can grow up without personally experiencing a direct hurricane landfall. Preparedness does not disappear overnight. It erodes quietly as memories become stories, emergency plans become paperwork, and the event people prepared for becomes something they assume will happen somewhere else. The water is going down in Indiana, and the lights are slowly coming back on in Hawaii. But the most important part of this story is only beginning. Damage assessments will determine how much rebuilding is required. Insurance claims will reveal where financial protection fails. Engineers will examine roads, bridges, levees, drainage systems, and transmission lines. Officials will debate whether maps, standards, and emergency plans need to change. Those decisions will take years, while the infrastructure built from them may remain for decades. 2 disasters struck America in the same weekend, separated by thousands of miles and driven by entirely different atmospheric mechanisms. Yet both expose the same uncomfortable reality. The past is useful for understanding risk, but it is not a guarantee of the future. A record that survives for 113 years can fall. A Category 1 hurricane that never officially makes landfall can still devastate communities. And a forecast can be completely correct, while people remain dangerously vulnerable. The water will eventually disappear from the streets. The damaged roads will be rebuilt. The power will return. But the numbers that were broken this week will remain. They will become new reference points for engineers, emergency managers, insurers, and communities deciding what comes next. The real question is not whether these disasters were unprecedented. It is whether America will treat them as warnings about the limits of its old assumptions, or simply wait for the next record to show just how far those assumptions were from reality.